Hello guys, welcome back to my channel, and today I'm going to be doing a special integral which was apparently asked in one of the Putnam exams and is probably the easiest question uh, that you can ask on this hard Putnam exam. But in any case, let's just not categorize our integral as easy or difficult just yet. I mean, we should never categorize an integral as easy and difficult, to be honest. But so let's get to it without much delay. So we have our problem. Let's call it I. This is defined as the integral from 0 to 1 of natural log of 1 plus x divided by 1 plus x squared dx. And this integral has a special name. It's called Serret integral. Or actually Serret integral. There's no apostrophe s. So now if you want to think independently, you can go ahead and pause the video and try to evaluate or simplify this integrand on your own. And you may notice after resuming the video that integration by parts fails because we'll just obtain a inverse tangent of x divided by x plus 1, so that's no good. And say if you try to do complex analysis, that would instantly fail because look at our upper and lower bounds. There is no infinity, right? This is not an improper integral. Complex analysis is excellent for improper integrals. And well, I don't know about Laplace transform and the Fourier transform. You can probably try evaluating this integral on your own using that. But the method that we are going to use and that works is Leibniz rule. But the challenge here, even in the Leibniz rule, is choosing the right parameterization. So I might discuss briefly what parameterization works and what doesn't. So let's explore the parameterization aspect of our integral on a fresh page. See you there. So we have our integral I, defined as the integral from 0 to 1 of natural log of 1 plus x divided by 1 plus x squared dx. And now if you remember this video of sine of x over x integrated from 0 to infinity, there if you remember we introduced an exponential term and used that as a fresh function which had the parameter inside the argument. That's because sine x is the limit as x tends to infinity of sine of x is non-existent because sine just keeps oscillating. But if we try to do that over here, so I'll just use another color. So if we just try to do that here, we need to get rid of this argument, right? So 1 plus x squared now. If we then try to differentiate this, we would definitely get rid of this term in the denominator. We would end up with integral from 0 to 1 of natural log of 1 plus x times e raised to negative, multiplying everything, t times e raised to negative tx squared dx. And there are many issues with this term, because now e raised to negative t is still a constant, so we can take it out. But this other term and this some sort of semi-Gaussian type of integral that we have here, and it's not even Gaussian because it's the upper and lower bounds are from 0 to 1, not 0 to infinity, so it's not even Gaussian. So it's not Gaussian. We can't use any of those properties of the gamma function, the beta function, the digamma function, or any of those functions, because this is a proper integral. It's not an improper integral. So there we end up with a problem. So this parameterization fails miserably. Now another parameterization that evidently fails is the natural log of t times whatever was inside 1 plus x, basically, while it's being multiplied. So this fails because using the log properties, now we have the natural log of t divided by 1 plus x squared plus, well, I just didn't write the denominator over here, but we have still the denominator. So, and the natural log of 1 plus x divided by 1 plus x squared dx. And this is pretty hard to work with, because we're again obtaining our I, and this is just a natural log term, right? So fine, we may get past our I prime of t step, because this is I of t, but when we take I prime of t, well, this just doesn't have an a t term, so this goes to 0. This becomes natural log of t with differentiated with respect to t is 1 over t times the integral of dx over 1 plus x squared from 0 to 1. And fine, this will become the inverse tangent evaluated from 0 to 1, which is pi over 4. So it will just be pi over 4 times 1 over t, fine. But when we reintegrate, we're going to have to integrate from absurd values, because we need such a value for t that will make the entire natural log term go to 0. So that is only possible when this inner argument is equal to 1, and equating that to 1, we have to introduce another variable. So t will have to equal 1 over 1 plus x, and we can't have a variable in terms of x for our reintegration step in the upper and lower bound. That's just absurd. We can have numeric values, but we can't have these variable values. That's just flawed technique right there. So even this parameterization is evidently failing miserably. So now let me show you what really works. So one parameterization that works, I mean, there are actually two, or I don't know how many more, but the two prominent ones I know is if you have the natural log of t plus x and the denominator as it is. That's option number 1. Option number 2 is natural log of 1 plus x times t. So these are two parameterizations that work, and while I'm actually evaluating or differentiating with respect to t each of the parameterized integrals, I'll briefly explain why they work. So in this video I would like to stick with option number 2. So let's go ahead and use that. So now consider I of t to be the integral from 0 to 1 of the natural log of 1 plus x times t divided by 1 plus x squared dx. And now it's time to differentiate with respect to t. So we have d over dt of I of t being equal to the d over dt of the integral from 0 to 1 of natural log of 1 plus x times t divided by 1 plus x squared dx. Now, since this is a special case of the Leibniz rule because the upper and lower bounds do not depend on t, we can just differentiate inside the integral sign to have a partial derivative with respect to t of the natural log of 1 plus xt divided by 1 plus x squared, and the differential operators are acting on this dx. So now, in with respect to t, 1 over x squared is a constant, so that's just as it is 1 plus x squared. And when we differentiate this, we have to use the chain rule, so that we have to basically include the derivative of this thing with the inner function intact. So that will be 1 plus x times t, and then when we differentiate 1 plus x times t, x is a constant, 1 differentiated with respect to t is 0, so we just have a simple x because t gets differentiated dx. So that's exactly what you get when you do I prime. This will be I prime of t using a Newtonian notation. Now I prime of t. So now why this parameterization works is because when we differentiate the natural log, we get this 1 plus x times t expression as it is unchanged, and we just get a simpleton x on top because we have to, this parameterization works because we had to use or rely on the chain rule. So a good parameterization is in most cases the one which relies on the chain rule. So a good parameterization often relies on the chain rule, because if you remember our integral from of sine x over x, we relied on the chain rule of e raised to negative tx. So we have obtained the exponential function as it is times this negative x factor when we were differentiating with respect to t. So a good parameterization, I repeat, is one that relies on the chain rule in most cases. That may not be always, but in most cases it does. So that's why both of our option 1 and option 2 of good parameterization work, because they rely on the chain rule, and they exploit the fact that the derivative of the natural log is just the reciprocal of the inside function. In other cases, this was clearly not the case, and we were obtaining bad forms of our parameterized integral. So that's why this thing works. It's actually a matter of intuition. If you keep on practicing, you'll eventually get a sense of what parameterizations work, what don't work. And now, since explaining the choice of parameters was the hardest part of the video, let's just go forward with what we do in any good old-fashioned Leibniz rule question. So now notice that we have a product of two factors in the denominator and a singleton x term. So it may seem like it's a good time to perform partial fraction decomposition, and if you're thinking that, you're going in the right direction. So I would like to perform this partial fraction PFD on a fresh page. See you there. So previously we obtained I prime of t is equal to the integral from 0 to 1 of x divided by 1 plus x times t times 1 plus x squared and a dx here. So forget the integral for now. We just have to perform partial fraction decomposition on the integrand. Just forgetting about the integral for now. We can reintegrate both sides with respect to x later on, finally, when after we've completed our PFD. So we have x over, just looking at the integrand now, 1 plus x times t times 1 plus x squared, and we want to split this in terms of two factors. So first factor is 1 plus x times t, and the numerator will always have a degree of 1 less than the degree of the denominator. So the degree of the denominator is 1 because it's a linear term, so the numerator should have degree 0, or it should be a constant. So let's call that a, which is a constant, plus, and now we have the second factor, 1 plus x squared. Now since the degree of the denominator is 2, the degree of the numerator should be 1 less than the denominator. So we should have a linear term in the numerator, and a linear term is always of the form bx plus c, where b and c are constants, and b is the coefficient of x, which is not, and b can't be 0, otherwise it won't be a linear term. Fair enough. Cross multiplying both sides, we have x divided by 1 plus xt times 1 plus x squared, and here we have a times this factor 1 plus x squared plus bx plus c times 1 plus x times t divided by 1 plus xt multiplied by 1 plus x squared. Notice these cancel out nicely, and we are only left with x equals a plus ax squared plus bx plus btx squared plus c plus ctx. So let's group all the x squared terms, all the x terms, and all the constant terms. So we have x squared as we can take as common times a plus bt plus x times b plus ct. So we got rid of this term, this term, this term, and this term, and only the constants a plus c are left. So plus a plus c. Now notice that the coefficient, there is no x squared term here, right? So the coefficient of x squared should be 0. A plus bt must be 0, and since there is no constant term here, a plus c must also be equal to 0, and since we only have 1 times x, so the coefficient of x must be 1. That means b plus ct must equal 1. So now we obtain a is equal to negative bt, a is equal to negative c, and over here we have c equals bt. That's after basically combining this equation with this equation, we get c is equal to bt, and b is nothing but c by t. So we now plug this b value into this equation. So we have c by t plus ct equals 1. We can cross multiply. We have c plus ct squared equals t. Factoring out the c, we have 1 plus t squared equals t, and therefore c equals t divided by 1 plus t squared. Since a is equal to negative c, so a is nothing but negative t over 1 plus t squared. B is nothing but c over t, so we just cancel out the numerator t. When we divide by t, we just obtain 1 over 1 plus t squared. So now, using all this information to basically decompose our original integral, let's go ahead and plug everything back in over here. So now according to our partial fraction decomposition, we have a equals negative t divided by 1 plus t squared. I'm writing the fraction in the numerator like this, divided by 1 plus x times t, plus b is just 1 over 1 plus t squared, that's multiplied with x, plus c, which is just t divided by 1 plus t squared, like that, divided by 1 plus x squared. So let's just write this properly now. We have negative t divided by 1 plus t squared times 1 over 1 plus xt. We can factorize out the 1 over 1 plus t squared term from everything. So we have 1 over 1 plus t squared factorized out, x plus t divided by 1 plus x squared. Fair enough. So that's our partial fraction decomposition. Now, as I promised, let's reintegrate both sides from with respect to x from 0 to 1. So I'm just writing that for your understanding. So basically, when we integrate both sides, even the integral gets carried over to this portion. So integral from 0 to 1, there is a dt. Integral from 0 to 1, we have a dt here. We just probably bracket this if you want. Well, fair enough. This is basically our I prime of t term, right? So that's our I prime of t term. Let's actually go ahead and simplify this big time. So we have this outside the integral, negative t is a constant divided by 1 plus t squared, everything is a constant outside the integral. We have the integral from 0 to 1 of 1 over 1 plus x times t dt, and now we have this outside the integral, we have plus 1 over 1 plus t squared times, we can split this into two integrals, integral from 0 to 1 of this, sorry, this is dx, my bad, x divided by 1 plus x squared dx, plus this 1 over 1 plus t squared factor is going to be as it is, 1 over 1 plus t squared times the integral from 0 to 1 of, well, now we can take the t out too, right? So t outside, integral of 1 over 1 plus x squared dx. So now let's go ahead and simplify them, or basically integrate them definitely one by one. So here we have negative t divided by 1 plus t squared. Why don't I factorize out a t from everything? So I have t factorized out, integral from 0 to 1 of 1 over t plus x dx, plus, now over here notice that the derivative of the denominator is just 2x, right? So we can recreate the derivative by multiplying and dividing by 2 like this. So we have the derivative of the denominator, and that basically just by our formulas of anti-differentiation just becomes the natural log of the denominator. So we have 1 over 2 times 1 plus t squared times the antiderivative is just the natural log of 1 plus x squared evaluated from 0 to 1, and now this is going to be t over 1 plus t squared times the inverse tangent of x evaluated from 0 to 1. Well, the t's are going to cancel out certainly, and we end up with negative 1 over 1 plus t squared, and you can do a u sub here, and in the end I'll just skip to what we finally get natural log of 1 plus xt evaluated from 0 to 1. So it's time to evaluate this from 0 to 1. So let's plug in 1. So 1 over 2 times 1 plus t squared times the natural log of 1 plus 1, which is 2, minus natural log of 1 plus t over 1 plus t squared times inverse tangent of 1 minus inverse tangent of 0. Now notice that the natural log of 1 is 0, inverse tangent of 0 is 0, and in the end we still have to evaluate this, right? So we had to plug 1 in the place of x. So we finally get negative natural log of 1 plus 1 times t, or just t, divided by 1 plus t squared, and when we plug in 0 in the place of x, we have 1 plus 0, which is 1, and natural log of 1 is 0. So for the second term everything becomes 0, so we don't bother about that. And for the next term now we have 1 over 2 times 1 plus t squared times the natural log of 2, because this thing just disappeared to 0, plus the inverse tangent of 1 is pi over 4. So t divided by 1 plus t squared times pi over 4. So that's basically your simplified version of I prime of t. And now we have to integrate this with respect to t from respectable upper and lower bounds, so that we arrive at a convenient form. And I'll show you in a bit. See you on a fresh page. So for finding a respectable upper and lower bounds for reintegration with respect to t, let's first look at our I of t. So our I of t was the integral from 0 to 1 of the natural log of 1 plus x times the parameter t divided by 1 plus x squared dx. So how does that relate to our original problem I? So now notice that when you plug in t equals 1 in I of t, that just becomes our I, right? Because then we'll have x times 1, so 1 plus x divided by 1 plus, so we'll just have our I, which is integral from 0 to 1 of natural log of 1 plus x divided by 1 plus x squared dx. That is the Serret integral. And now notice that when you plug in t equals 0, you're going to have the integral from 0 to 1 of the natural log of 1 plus x times 0 is 0, so natural log of 1 divided by 1 plus x squared dx. And now look at the genius behind this. Natural log of 1 is 0, so everything just becomes 0. Therefore when we integrate I prime of t from t equals 0 to t equals 1, we're going to have, by the fundamental theorem of calculus, I of t when t equals 1 minus I of t when t equals 0, and I of t when t equals 1 is just our I, right, our Serret integral. So I minus I of t when t equals 0 is 0, so I minus 1, or just I. And we know I prime of t, right? We just calculated this in our previous section of after performing our partial fraction decomposition, we got a simplified expression of I prime of t. So we just need to integrate that now with respect to t from t equals 0 to t equals 1. So let's do that now, because that will just evaluate to I just showed that to you. So we have our I prime of t. Let's just integrate that from with respect to t from t equals 0 to t equals 1. So when we do that, this will just be I of t. I just showed you a moment ago. I of t, I prime of t will just be I. Sorry, I just showed that to you a moment ago, because that will be I of t when t equals 1 minus I of t when t equals 0. I of t when t equals 1 is I, and I of t when t equals 0 is 0. So we just obtain I, our original Serret integral, our original problem, and we still have to integrate this side. So we have negative integral from 0 to 1, natural log of 1 plus t divided by 1 plus t squared dt. It's an integral with respect to t now, and we have natural log of 2 divided by 2 times integral from 0 to 1 of 1 over 1 plus t squared dt plus pi over 4 times integral from 0 to 1 of t divided by 1 plus t squared dt. And now notice that this is just our Serret's integral, or just I. It's just that instead of x we have a t, and that doesn't change the entire meaning of the integral, right? That's one of the properties of definite integration. As long as you have the same upper and lower bounds and you have the same integrand, but there's a change of variable, then the meaning of the integral is intact. So that's nothing but, we have a negative sign, and this is nothing but I, because I was our Serret integral. And over here we have natural log of 2 divided by 2 times inverse tangent of t evaluated from t equals 1 to t equals 0. And now notice we can recreate the derivative of the denominator on top, so multiplying and dividing by 2. So 2 times 4 is 8, so pi over 8, and the entire derivative of this thing is just the natural log of the denominator now, because we match the derivative of the denominator on top. So this is the natural log of 1 plus t squared evaluated from t equals 1 to t equals 0. So in the end we can add this I to that side. We get 2i is equal to natural log of 2 divided by 2 as a constant. We can factorize that out, times the inverse tangent of 1 minus the inverse tangent of 0 plus pi over 8 times, when we plug t equals 1 here, we have the natural log of 1 plus 1, or 2, minus the natural log, when t equals 0 we have a natural log of 1, like that. Now notice that the natural log of 1 is 0 like before, inverse tangent of 0 is 0. So finally we obtain 2i is nothing but natural log of 2 divided by 2 times inverse tangent of 1 is pi over 4 plus pi times natural log of 2 divided by 8. You can simplify this out now. We have a 8 in the denominator, so we have pi times natural log of 2 divided by 8 plus same thing, pi times natural log of 2 divided by 8, which will be pi times natural log of 2 divided by 4, But now notice that this is just 2i, so let's divide both sides by 2. So we have I is equal to pi times the natural log of 2 divided by 4 times 2, which is 8. So that's what your original problem I evaluates to. So that's the value of our Serret integral. So as a formality, here I defined as integral from 0 to 1 of the natural log of 1 plus x divided by 1 plus x squared dx, and that we chose a right parameter before using Leibniz rule. We differentiated both sides with respect to t and then reintegrated from appropriate upper and lower bounds of t, and then we ended up with a value of pi times natural log of 2 divided by 8. And that's a pretty neat formula because the pi just drops in again out of nowhere, and there were no trigonometric terms here, so it's truly out of nowhere if you ask me. And so that's your Serret integral, or rather, if you wanna say that it's a special case of the Serret integral, then so be it. It's a special case, but I'm going to do a more general version of the Serret integral in future videos. So stay tuned for that. But that's it for this video, guys. Please like, share, and subscribe to my channel. Recommend me to your friends, please. All the mathophiles and people who are interested in this kind of stuff. And please follow me on Instagram. I have the username gamma_digamma. I post math, art, and math related stuff. In the meantime, stay home, stay safe. Have a great day. Peace out.